Black holes, they're easily one of the most powerful and, let's be honest, mysterious things in the entire universe. They represent a point where our understanding of physics just completely falls apart. So, what we're going to do is take a journey to the very edge of reality itself. And that quote from Stephen Hawking, it really hits the nail on the head. I mean, think about it. Black holes are, by definition, a void. They don't give off any light, so how on earth could we ever prove they exist? This simple question really set the stage for one of the greatest detective stories in the history of science. All right, so here's our game plan for this explainer. We're going to start with how this whole idea was born, basically out of thin air. Then we'll get into the life and, more importantly, the death of a star. We'll dissect the anatomy of a black hole, hunt for these invisible monsters, and finally get into why they might just hold the key to, well, everything. Okay, first up, an idea born in darkness. And what's so incredible about black holes is that they were predicted long before we had any chance of actually finding one. They didn't start in a telescope, they started as a ghost in a math equation. The first little hint of this idea was planted way, way back in the 1780s by John Michell. But it took almost 200 years of work, from Chandrasekhar's super important calculations about dying stars, all the way to Hawking and Penrose predicting this infinitely dense point, before the theory really started to look like something real. So to really wrap your head around something as wild as a black hole, you've got to start with the life of a star. And a star's whole life? It's basically this constant, violent battle between two of the universe's most fundamental forces. Okay, so it all kicks off with gravity. You've got this massive cloud of hydrogen gas, and gravity starts pulling it all together, collapsing it in on itself. As it gets squeezed tighter and tighter, the pressure and temperature just go through the roof. Eventually, it gets so hot and crowded that hydrogen atoms literally start smashing into each other and fusing to create helium. And that's nuclear fusion. And this sets up this incredible cosmic tug-of-war that lasts for the star's entire life. You've got gravity on one side, just relentlessly trying to crush the star into the smallest point imaginable. And on the other side, you've got this massive outward explosion from the nuclear fusion in its core, pushing back. For billions of years, these two forces are locked in this perfect, stable balance. And we're talking about a colossal amount of energy being released here. Why? Because when hydrogen fuses into helium, a tiny, tiny bit of its mass gets converted directly into pure energy. And that's all thanks to Einstein's famous equation. This is literally what makes a star shine. But here's the thing, that fuel isn't going to last forever. And when that fusion engine in the star's core finally starts to sputter and die, that cosmic battle we talked about, it comes to a very, very dramatic end. So, a star spends its life fusing lighter elements into heavier ones, hydrogen into helium, helium into carbon, and on up the periodic table. But the whole process hits a dead end at iron. See, fusing iron doesn't release energy. It actually consumes it. So with no more fuel to burn, that outward push from fusion just stops. And gravity, that relentless inward force finally wins. The star starts to collapse. Now, for a smaller star, the collapse eventually gets stopped by something called electron repulsion. The result is what we call a white dwarf. It's an object about the size of Earth, but it's so dense that a single cubic inch of it, like a sugar cube's worth, would weigh hundreds of tons. Just incredible. Okay, but what if the star is bigger? Well, if it's more massive, gravity is strong enough to literally crush the electrons into the protons, and they form neutrons. The collapse is then stopped by the repulsion between these neutrons, and what you get is a neutron star. Now we're talking about the mass of our sun packed into a ball just 20 miles across. The density is insane, millions of tons per cubic inch. So we've seen that there are forces that can put the brakes on gravity's total collapse. But what happens if the star is so ridiculously massive that nothing can stop it? What happens when gravity is completely, totally unopposed? And that is how you get a black hole. When a truly monstrous star dies, gravity just steamrolls every other force in nature and crushes that star down to an infinitely small point. Right at the very center of a black hole is the singularity. This is that point of infinite density that Hawking and Penrose predicted. It's a place where space and time get so warped and twisted that all of our known laws of physics just break down. They don't apply anymore. And wrapped around that singularity is the event horizon. Now, you can think of this as the surface of the black hole, but it's not a physical surface you could touch. It's more like a boundary, a threshold. Once you cross the event horizon, gravity's pull is so intense that there is no escape. Not even for light, the fastest thing in the universe. It really is the ultimate point of no return. And this brings us to a pretty common myth I want to bust right now. The idea that black holes are like cosmic vacuum cleaners just sucking everything up. They're not. Their insane gravitational pull is only inescapable once you get really, really close. In fact, if you could magically replace our sun with a black hole of the exact same mass, you know what would happen to Earth's orbit? Absolutely nothing. We'd just keep on orbiting like normal. We'd just be very, very cold. Okay, so the theory was looking pretty solid. But how in the world do you find something that's literally invisible? Well, you don't look for the thing itself. You look for the chaos it creates around it. And the first really big suspect was an object called Cygnus X1. Astronomers started putting the pieces together, and they found 3 key clues. First, Cygnus X1 was just blasting out a ridiculous amount of X-rays. Second, they spotted this giant visible star that seemed to be, well, wobbling, like it was orbiting something they couldn't see. And third, they figured out that material was being ripped off that visible star and getting superheated as it spiraled toward its invisible dance partner. And that was what was generating all those X-rays. And here is the absolute clincher. By studying that wobble, astronomers could actually calculate the mass of the invisible partner. And it turned out to be 6 times the mass of our sun. That was way, way too massive to be a white dwarf or a neutron star. There was only one thing it could possibly be: a black hole. I mean, what a discovery. It was a huge triumph, but it was really just the beginning. It turns out black holes aren't just fascinating cosmic graveyards. They represent one of the deepest, most profound puzzles in all of science. And then Stephen Hawking came along and made this absolutely stunning discovery. Black holes aren't completely black. Because of some really weird quantum effects right near the event horizon, they actually leak a tiny, tiny amount of radiation. We call it Hawking radiation now. And what this means is that over unbelievable timescales, billions upon billions of years, a black hole can actually slowly evaporate and disappear. And this right here gets to the very heart of the ultimate mystery. You see, all of modern physics basically rests on 2 amazing theories. We have general relativity, which perfectly describes the universe of the very big, planets, stars, galaxies. And then we have quantum mechanics, which perfectly describes the universe of the very small, atoms and particles. The problem? The huge problem? These 2 theories are completely incompatible. They just don't play nicely together. Except, maybe, in one place: the singularity of a black hole. Think about it. It's a place that is both unbelievably massive, that's the world of general relativity, and at the same time infinitesimally small, that's the world of quantum mechanics. It is the one place in the entire known universe where these 2 giant theories have to meet, and that's why the hunt is on. Because if we can ever understand what's happening in that singularity, we might just unlock the theory of everything, a single elegant equation that explains the entire cosmos, the greatest triumph of human reason, right there for the taking.